that you can see some sort of like curvature in motion and then can do orbit determination. So without follow-ups, newly discovered asteroids can be lost due to large uncertainties that will keep growing over time. Meaning that we won't know their orbit accurately enough to say when and where they will be near Earth again in the future. So since there are so many asteroids, we prioritize again ones that are considered potentially hazardous or close to the size limit and still come very close to Earth's orbit. Another category we'd go after a lot from Arecibo was great NASA acronym here, NEAs, near Earth object, human spaceflight accessible target studies. So ones that in general take relatively less fuel to get to with the spacecraft mission, which generally means their orbits are fairly similar to Earth. So low inclination, low eccentricity, semi-major axis around 1 AU. Okay, so tracking asteroid discoveries over time. NASA has a mandate from Congress to find and track near-Earth objects larger than about 140 meters. This was not fully funded initially, but steadily making progress. So blue is near-Earth asteroids of all sizes. Orange is 140 meters and up, so we're up to close to 11,000 of those now. And red is 1 kilometer and up. Those have sort of leveled off. We're only finding a couple new ones every year. There's around 940, I think, total. So that's the discoveries. Radar is mainly for follow-up and characterization. And since people often ask about the impact hazard, this isn't my specialty, but I looked up the numbers last night. So statistically, based on estimates of the population, we think we're at more risk from ones that haven't been discovered yet, but out of the ones that have been discovered with well-determined orbits, top known risks are Bennu, which has about 1 chance in 1800 of impacting the Earth starting like 150 years from now. And then 1950 DA, which has about 1 chance in 30,000 of impacting the Earth in the 29th century. So Marshall Canada. Anyway, so good to know this, but I always tell people like we shouldn't run around like Chicken Little and overstate the impact risk, or no one will take us seriously if one actually is coming close. So I would say we're in the short term, we're in more danger from ourselves. So like the average person in the United States has about a 1% lifetime risk of dying in a car crash. That is much, much higher than your odds of dying from an asteroid spray by any estimate I've ever seen. So Bennu, you may recognize because that was the target of NASA's OSIRIS-REx mission, which visited and then just brought samples back a few months ago. So here's a close-up view of Bennu. So now we know the orbit much more accurately, thanks to having the spacecraft there. We have lots of detailed images. We know the shape, rotation state, all sorts of other stuff very accurately. And one of the reasons that asteroid was chosen was its high on the impact risk. So the OSIRIS-REx mission did not completely eliminate the impact risk, but at least we know much more about that asteroid if we need to knock it out of the way in the future. Okay. So hang on. So my laptop has this strange quirk that it gets unhappy if a single presentation file gets too large. So I need to switch to another file. I have to do this several times, but with me. Loading. Always important to us. Okay, and people online. Yeah. Okay. Okay. So radar. I spent a while talking about asteroids, so let's talk about what we can do with radar observations. So, what do we actually measure? So, one thing we can measure is frequency. So we transmit basically a sinusoid, a constant frequency. The echoes come back. So if you're measuring only frequency, you get more power effectively in the received echoes. So the Doppler shift in the received signal tells you the target's motion along the line of sight toward or away from you. However, if you're only doing the frequency measurement, you don't get distance information. In order to get that, there needs to be some sort of time structure in the signal that goes out. So either vary the phases or vary the frequencies that are being transmitted. So often we'll start with frequency only to make sure we can actually see the asteroid and switch to something more complicated. Okay, so here's my prop. So if you're looking at the video for the people online, imagine that this is an asteroid. Use your imagination. So the asteroid's rotating, so it's the center of mass is moving toward you or away from you, but also it's rotating. So this part is rotating toward you, this part's rotating away from you. So this part gets slightly blue shifted relative to the center of mass. This part gets slightly red shifted. So if you're transmitting a single frequency, the echoes you get back are still smeared out in frequency. So here's an example of that. This is 1999 KW4 binary asteroid, which now has a name, Moshe. The spike there is from a satellite. So I'll talk about the bandwidth. Bandwidth is like how many hertz wide is the signal. So that's telling you something about the size and rotation state of the asteroid. Okay, so a couple other examples. Lisa's favorite, 2019 OK. So in this case, this one, 2019 OK has a bandwidth of about 40 hertz. Signal goes from like +10 to +50. This other one, JU3, has a bandwidth of like less than 1 hertz. So there's the equation for bandwidth in the top right. So greater diameter gives you a greater bandwidth. Faster faster rotation period, so smaller p also gives you greater bandwidth. It also depends on the viewing geometry. So if you're observing it, if your line of sight is close to the asteroid's equatorial plane, you'll see the greatest possible variation. On the other hand, if your line of sight lines up with the rotation axis, there's no differential motion along the line of sight. So the signal we see is compressed in a very small range of frequencies. Okay, so from each detection, we get spectrometry. So where the signal is centered. So if the signal was centered at 0, that would mean our ephemeris was perfect. In reality, this is 2019 OK. We observed it shortly after it was discovered. So there's like 30 hertz offset. It's telling you about radial velocity. So you can use that to get a more accurate orbit. Again, the bandwidth is telling you about combination of the size and rotation period, but those are like jumbled together. So you can't disentangle that with just a single measurement.
Can you try to take out the?
And he has to do it.
Oh,
Can you take that
sorry.
off?
Moved it
Thank
before-
you.
I moved it, but it moved back. Yeah, sorry. Okay, right. So anyway, the area under the curve, so total echo power is radar cross section after you do the calibration, which tells you something about the size and radar albedo of the asteroid. Okay, so if you have some sort of time structure in the signal that goes out, you can also measure delay. So you can imagine transmit a pulse of radar waves. Yes.
Short question, you mentioned radar albedo?
Yeah.
Is that albedo related to the visible albedo or that is a different?
It's, well, same principle, but it's different wavelength. So what fraction of power gets reflected at the
But there is no
wavelength of the
relation
radar.
between them or there is a relation?
Sort of, like different spectral classes have different radar albedo. That's
Oh,
like
okay.
another talk. Yes.
Sorry, I know just a little bit about radar. I was wondering if the echo signal that you mentioned, it's emitted and then goes back, right? Is always the same power, I mean, the same signal for every asteroid? Or
No,
they configure that?
not quite. I'll come to that, but yeah, effectively we can adjust the signal that goes out within the limitations of the system based on what we think will be most useful. So yeah, for most of astronomy, whatever light comes in, that's what you get. Radar is different. We control the signal. So yeah, radar is magical. So you can imagine transmit a pulse of radio waves, then wait to see how long it comes back. In reality, we want to be transmitting continuously, but if there's time variation in the signal that goes out, we can recover that information, get the exact travel time, the echoes that we record. So measure it to a microsecond accuracy or better. So that's get the distance within hundreds of meters for something that can be millions of kilometers away. So again, most of astronomy distance is hard to get, but in this case, basically getting it directly. So that also helps a lot with determining the orbit more accurately. So I mentioned measure frequency, measure time. Why not do both? So if you have a target that's sufficiently close and large, you can resolve the echoes in so frequency along the horizontal axis for all the images that I'll show, delay along the vertical axis. In this case, this is 1998 QE2. The big one is the primary, and the little blur there is a little satellite. So binaries are fun because you can get the mass of the system from measuring the orbital period and the separation. Here's another one. This looks like two separate objects, but it's actually one near-Earth asteroid with multiple lobes. You just can't really see the joint in this particular image. 2005 NC6. Another binary, 2004 BL86. This one was observed from Goldstone. It's 2015. Okay, yeah, switch gears, animation. So we had this image posted on the Arecibo website, which unfortunately is no longer a thing. So let me push it here.
You're sharing the full screen with the people in the room?
Not yet. Okay, so this is an animation of the binary asteroid 1999 KW4. So these animations are sort of the best thing I've ever seen for building some intuition for how to interpret the radar images. They look like grainy optical images, but they're not. So what the radar image looks like is not necessarily what your eye would see. So on the right is the plane of sky view of the primary and satellite. On the left is the simulated radar image. It's not showing up that well here, but anyway, so you can see the satellite moves around, goes to the top. So here's closest to the observer. Now it starts moving away. And eventually you see the satellite disappear when it goes behind the primary there. So anyway, yeah, and so the horizontal axis is proportional to, again, speed along the line of sight, which is not directly the same as like the physical extent. So you'll see the satellite only has a narrow range of frequencies that it can move around in, and sometimes appears to overlap the primary. It's just how radar is complicated. Yes, Luisa.
How many days of data, if you know, has that animation has?
Oh, well, I mean, this is just simulating for like a few hours. Well, okay, it's a simulating full orbit of the satellite, which is probably like 10 hours, 20 hours or something.
But on the left, because on the left is the actual data.
No, the data are simulated. This is based on like actual radar observations, but here the simulated images conveniently don't have noise.
So on the left is also simulated.
Yeah. So yeah. if you
And
look
were
at-
these shape models done with both radar and light curve data? Or just
This
radar?
one, yes, I think so. So yeah, I talk about radar, but whenever we can get light curves or anything else, we want to use those as well. Anyway, if if anyone wants this animation, email me and I can send it to you. I have permission to share it. And again, eventually it'll be posted on the website once we've got our website running. Okay. Okay, back to our regularly scheduled programs. So keep telling myself I should get a new laptop, which hopefully won't have these issues, but I haven't done it yet, so.
Mac.
Overrated. Well, let's argue about that later.
Not really.
All right, that's another hour or so of conversation. So maybe some other time.
Maybe for one of
Or-
the Thursday
Or many hours, yes, sounds like fun. All right, so different radar facilities. So this is Goldstone, 70-meter diameter in California. So Goldstone is part of NASA's Deep Space Network. This is the largest single dish, that's the best radar transmitter. Transmits up to 0.5 megawatt at about 8.5 gigahertz or 3.5 centimeters. This one's fully steerable. Oh, yeah, there's like a truck down there for scale, which you can't see that well. Again, it's 70 meters, so close to the size of a football field. Or soccer, if you like. However, as one of our colleagues likes to say, Goldstone has a day job, so they spend most of their time doing spacecraft communication for NASA's interplanetary missions. So they can only spend a small fraction of their time actually observing asteroids. Plus, it's hard for them to observe asteroids on short notice. So that involves like bumping someone else off the schedule. We've got a little more flexible with that in the past few years, but still, it's a limitation, not from the technical side, but directly, but in the logistics. Also, so NASA other deep space network station is in Australia, near Canberra. So we'll transmit from the Canberra 70-meter dish, which is more or less identical to the one at Goldstone, and then receive the echoes, usually with the Australian telescope compact array, which is like I think 5 or 6 dishes around 30 meters in diameter. And maybe question.
Do the three of those antennas have emitters?
I think they all do, but they're not that powerful. So Goldstone can go up to like 500 kilowatts. The best one they have here, I think, is like 80 kilowatts.
So they don't work together, they don't emit the three at the same time to the same time.
Okay, radar arrays are another issue. So JPL did some tests with that at Goldstone, and we're looking into doing similar prototypes here, but these ones don't work that way. So yeah, you need to like link them together so that the transmitted signal is phased up properly. So complicated, but that's the future. That's how you get to more transmitter. So also this is in the southern hemisphere, so you can see parts of the southern sky that are not accessible with Goldstone. Or from Arecibo. So yeah, Arecibo no longer available, unfortunately, but still the best planetary radar system we've ever had. 300 meters across, we can go up to around 900 kilowatts under ideal conditions, work at a slightly lower frequency. Again, it's so big that you couldn't actually move the dish. You control what you're pointing up by moving the dome up there. So that meant declination range was limited. But in practice, that wasn't too bad for asteroids because most of them at some point will pass through Arecibo's declination range, even if they couldn't get it right during close approach. So for Arecibo, we could get up to, our best was 126 near-Earth asteroids in calendar year 2019. Comparison, I think Goldstone did like 60 one year, which is about their best. So yeah, Arecibo, we miss it. So here's a picture of Team Radar, 2020, late 2020 during the pandemic. So we all have masks. This was before Moran got there. We should do a new group photo sometimes.
Yeah. Closer together.
Yeah, inside, yeah, since
Oh,
that's
wow.
less of a concern there. Here's control room in Arecibo, just like showing this, with the intimidating wall of cables in the background. And of course, yeah, 2020 so we already had to deal with like earthquakes, plus the pandemic and tropical storms, then finally the telescope collapsed, so. But still the leader for near-Earth asteroid detections by radar. We got over 800. And Goldstone will take quite a while to catch up to that. Okay, so switching gears here, other file, any questions on switching files?
Similar collecting area and the whole thing. But it does not generate yet publicly.
Is this fast?
Yes.
Yeah.
Yeah, they can't get a radar on the planet. It's too heavy. The
No.
transmitter is too
Yes.
heavy.
And
In theory, they could receive echoes from somewhere else, but then they're not gaining like the full collecting area for both parts, transmitting and receiving, only one way.
And the radar was not only used for planetary Arecibo, it was also used for the study of the atmosphere, the ionosphere, and that was one of the powerful.
That was the first.
Areas
idea,
also.
actually. Okay, it wasn't my idea in the beginning.
When
At the
they
beginning,
started,
yeah.
it was an ionospheric, observatory.
Mhm.
With the purpose of just really intercepting telecommunication signals
Yeah.
during the war times. And then eventually it expanded more and transmitted to the moon, the moon bounces. Simple sending signal to the moon.
Okay, so now jumping into a specific application of the radar data. So shape models, so I showed some images from some of our asteroid radar highlights, so we can't get images like that for every single target. Basically, if you're trying to resolve the signal like this, basically the total power you get back is more or less constant no matter what observing mode you're using. So if you try to split the signal into more and more pixels, they get fainter and fainter individually. But for the best and brightest targets, we can get nice resolved images. We'll talk about one of my favorites. This is asteroid 1999 JD6, also called the Space Peanut in the JPL press release. So yeah, and again, it takes many people to do all these observations. So in this case, for this asteroid, we have radar observations from Arecibo and Goldstone, plus light curve observations from people on several different continents. That's most of the co-authors there. So yeah, optical light curves, again, many of you do these observations, but so for an elongated object, especially like 1999 JD6, so if you imagine you're on Earth, you're looking at the asteroid, let's say the sun is straight behind you, so low phase angle. If you're seeing the asteroid like this, there's a larger area that's illuminated and facing you, so it looks brighter. Quarter rotation later, you're seeing the minimum projected area, it looks fainter, brighter, fainter. So for an elongated object, you get 2 minima and 2 maxima in the brightness for every rotation. So from that, we get the rotation period. This one had light curve observations going back to around the time it was discovered in 1999 and several apparitions later. So we already knew before any radar rotation periods around 7.7 hours. Yeah, more light curves. So radar, this one had a more distant approach in 2010, but the best close approach was 2015. So there were 3 days of Arecibo observations in 2010, 6 days in 2015. I went down there for those during grad school, so I wanted to adopt this asteroid basically. And then we also got it 1 day in 2020 during more distant close approach. This is one of the last ones we got actually. So transmit the signal, echoes come back. So we also had, Arecibo observations, Goldstone observations, and on, I think, one night they had Goldstone teaming up, transmit, and the echoes were received at the Green Bank Telescope in West Virginia. The telescopes on here are more or less to scale, as close as I could get them, so give or take a couple pixels. So, great coverage, a lot of different viewing geometries here. So this is part of the right ascension declination of JD6 during the different observations from Arecibo, Goldstone, and triangles, and then light curve observations or the blue circles. So in general, this is good because we get much better constraints in the rotation state. So sometimes we're seeing it sort of broadside, sometimes we're seeing it close to pole on, given many different days. You can constrain that much more easily than otherwise. The previous asteroid I worked with was 2000 ET70, which only had like a week or so of light curve observations, and getting the pole direction for that one was really tricky. So between that and JD6, I'm saying the pole direction karma is sort of balanced out. Anyway, so stepping through the radar observations, first day from Arecibo was relatively distant, so like 1/8 of an AU. Get CW spectrum, but that's about it. No clear images. Okay, and then first night they got it from Goldstone, actually saw a very narrow band. So basically, so there's the bandwidth equation again. So the diameter and the rotation period can't change on like a small time scale. So that means, so phi is the angle between your line of sight and the equatorial plane, or so subradar latitude basically. So in this case, we were seeing it very close to pole on, within like 2 degrees, I eventually figured out. So you saw a very narrow bandwidth. So it was like 1 hertz wide from Goldstone versus like 8 hertz wide from Arecibo. And then anyways, that's what the shape model from later on. So there's the plane of sky view for that particular night. Great. So again, knowing that it was very close to the line of sight lined up with pole during that night helps a lot with determining the pole direction. So there's the sort of not the sort of the opposite direction for the pole vector. So yeah, it lines up with that match with Goldstone. So yay. Okay, so the highlight, night of closest approach, it was too far north for Arecibo, but Goldstone and GBT got a nice sequence of images spanning like 8 hours. Yeah, almost 8 hours, so close to a full rotation. So again, called it Space Peanut in the press release. I'm allergic to peanuts, so that made me smile since this is like my asteroid.
And you're
But I-
watching the peanuts.
Yeah, and so I have extra incentive to make sure it doesn't come close to Earth and make sure that we know as much about it as possible. Anyway, so with the shape models, we start with something simple and work our way up. So I tried spherical harmonic initially, two ovoids, not quite overlapping, which, you know, I had issues when I tried to connect the two. But yeah, work up to something more complicated. So early stage sort of looks like a bowling pin, but I wasn't sure that I had the joint right. Also, there was a spike there that seemed questionable. Oh yeah, and so this is around 3 kilometers long maximum. And the average diameter is around 1.4 kilometers. So yeah, just start simple, gradually work up to more complicated models. Yellow fading means that region wasn't seen well during the radar observations. It's more uncertain. It's like a weird chunk there that didn't seem quite right. So the software requires some human intervention to guide it toward reasonable results. So parts of that are in R as much as science. So near the end, oh yeah, and usually the final models are represented as triangular mesh. So here we can see the individual triangles. So typically a order like 1,000 vertices. Okay, so near the end, yeah, rotation period, we know very, very accurately because I found there was a unique solution linking up the light curves from all the different years from, I think, 1999 through 2015. So we know exactly how many times it rotated within a few degrees during that like 16-year arc of data. About the pole direction very, very accurately. So usually with the radar and light curves, the uncertainty of the pole direction is around 10 degrees. In this case, I got lucky with the viewing geometry, so I got it to a fraction of a degree. Yay. Final shape model. Oh yeah, and sometimes again, the shape modeling software has issues. So in this case, I have like one facet folded over another facet and didn't realize that before I tried running the fits. That resulted in the software got confused and had like a spike sticking out like that. So real asteroids don't look like that. So anyway, once I realized what happened, it was a relatively easy fix, just didn't catch it beforehand. Oh well. Okay, so comparison for the final model. So I'll have data frames on the left, model frames in the middle. So the goal is to get this to match this as close as possible, and then simulated plain sky views on the right. So you can see sort of two bright edges there from the two lobes. Model does that, yay. Yeah, this is from the best night with GBT. So, yeah, and the joint is a little tricky because it's hard to tell like how sharp the concavity should be since you don't get a strong reflection from right in there because none of the facets are pointed right toward you. So that requires some trial and error and experimenting with different things. This is from Arecibo, so it's getting fainter, it's just moving away by this point. So yeah. A shape. And also you may wonder, can we actually trust these results? So, and the answer based on OSIRIS-REx is yes, we think so, because they did very well with shape model for Bennu based on mostly Arecibo observations from 1999, plus a couple like farther apparitions later on. But with Bennu, they got the size and shape just about right. Pole direction was within a few degrees. Even one of the largest boulders on Bennu was seen as like a bright spot rotating across some of the radar, which is. So we think we know what we're doing, so it gives me hope for the future. Hope for my job security since I'm working on another spacecraft target, which that's Phaethon, which I'm not showing here, but we show that hopefully some other presentation once the paper is finally done. Okay, which time is that? Okay, good. So one last
Do you have an idea when you look for that? How many binary asteroids have a shape model with radar? Using radar, not
yeah, a dozen or so.
those.
Yeah.
Using both.
Radar, so yeah, again, I'm focusing on radar, but almost everything with radar observations will have light curves as
Yeah.
well, or at least for the shape modeling.
90%.
Yeah, for the shape modeling, we have more good targets to choose from, good targets with radar data. Like we're taking the data faster than we could do the analysis. And even now, like we're not doing the new observations, but there's still a backlog. So in practice, when we're deciding which ones we want to work on, we'll generally choose something that has light curves as well as
Yeah.
radar. Okay, so working for the future here, final was. Okay, so. Anyway, so with Arecibo gone, we'd like to move that far out of the way. We'd like to get something bigger and better eventually. So can't get that overnight, so part of supporting that, so this is something I've worked on over the past year, going through the numbers. So how many near-Earth asteroids could we actually detect with different radar systems? So again, here's Arecibo and Goldstone to scale. All right, so yeah, goal again, figure out how many near-Earth asteroids and various like subclasses of them, like potentially hazardous, we could detect with different planetary radar systems. So I worked through the numbers using the system specs for systems from the past, Arecibo, present, Goldstone, and Canberra in Australia, and possible future systems that we've at least thought about. So NGAT plus Green Bank transmitting to the NGVLA. So it's just following up on some work, especially by Shantanu Naidu, worked through the numbers in paper in 2016. So again, there's more asteroids being discovered now, and we have new systems that we're considering. So I wanted to revisit this. And we did like some preliminary versions of this for Anisha's NGAT papers, also presentations by Flav and me at conferences last year. So system parameters, if anyone's really curious about the numbers that went into this, book me later, but so after pondering this for a while, sort of the best visualization we have for sort of illustrating like your reach into space or how many asteroids can you detect. One nice way of showing that is you pick like some asteroids, here I picked the standard 140 meters in size with like the average rotation period, so 2 hours right near the spin barrier. Radar albedo at 0.1, 10% is typical. And then show like in what region in space, so declination along the polar axis, and then distance along radial axis. So different shading is regions of the sky at which different facilities would be able to detect this particular asteroid. So definition of detectable for radar is signal to noise ratio greater than 5 in 30 minutes of observations. So in practice, we'd rarely, some cases we're going after newly discovered targets. We don't know the details about them that well. So sometimes it's like, okay, this one's like on the edge of what we can detect. So in practice, we don't see it within 30 minutes. We usually move on and try something else. So, and this is using latest version of NGAT with diameter, so array of dishes with diameter of around 130 meters. So the existing facilities, again, Canberra can see the southern sky, but they can't see very far out. Since they have lower transmitter power, Goldstone can do better, mainly because of greater transmitter power. Arecibo, best of anything so far, but again, limited in declination range. And the other facilities, so NGAT has slightly greater declination range as we envisioned it, can see basically down to declination -60 or so. Green Bank transmitting to the NGVLA in New Mexico has slightly better range, but slightly greater distance range, less declination range, so it's sort of a trade-off. Oh yeah, and okay, so simplifying assumptions. So yeah, I mentioned detectable means SNR of 5 in 30 minutes. Spherical asteroids, which most of them are not actually spherical, they're more interesting, but since we only have rough numbers for some of these, just sort of stick with the simple case. To get the cross section and the bandwidth, to figure out what's the actual signal noise ratio. That was based on fitting to cross sections and bandwidths reported by Yerke et al. 2022. So that was covering a few years of radar observations, I think like 190 objects. So it's a good sample to choose from. So in general, for a new discovery, basically the only thing we know going in is the H magnitude. So I need some way of scaling from that to the like average cross section and bandwidth based on the average properties from the ones we observed. Okay, so here's a simple example here. Detectable, potentially hazardous asteroids on one particular day. This is the end of April 2023. So dividing the SNR in several bins here. So green means bright enough for imaging, SNR greater than 50 in 30 minutes. So you can actually get the nice images. Blue, lighter blue is SNR between 10 and 50, so we can get a range measurement, but not detailed images. And then darker blue or purple is SNR of 5 to 10, so you can get CW detection, and that's it. So green is better. So for this particular example on this day, so Canberra could not see anything. DSS 14, Goldstone would be able to see one potentially hazardous asteroid. Arecibo, if it was still functioning, would have been able to see two of them, one CW only and one ranging. And then the future systems could each see, so it's like 11 for NGAT and 14 for GBT. Now, an important caveat here. This is saying how many are like within range such that we could detect them if we tried to do the observations. In reality, Arecibo could not spend all of its time doing asteroid observations. And like Greenbank to NGVLA, it turns out there are other astronomers who want to use GBT and NGVLA, so we would not, so there's this many asteroids potentially detectable on any given day they'd go after maybe one or two of them. But
Why is for SNR equals to 10, the GBT and NGAT has the same number?
oh, just happens to be similar. The capabilities for the two are similar. So on this particular day, they both have the same number above SNR F10, but it'll vary. So yeah, different plots here. So yeah. Okay, so this is rather than showing for each of the 5 facilities, showing for one facility at a time over a period of like 1 month, how many asteroids are detectable. So you see fluctuations, different categories here. So, oh yeah, also I have color coding for asteroids that were either lost, meaning the uncertainty, in theory, it was within range and detectable, but in practice, the uncertainties were too large and they wouldn't have been able to go after it. Black is undiscovered, so this was, so I ran these calculations like a year after the times shown here, so it turns out there were other asteroids that were within range, but they hadn't been discovered yet, so we can't count them. Since it's all NEAs, not just PHAs, so on average, Goldstone you can see around 3 on any given day. This is sort of zooming out along the time axis. This is showing 12 months. So for Goldstone, yeah, median 4 detectable NEAs on any given day. So you see there's some variation there. Some of it's monthly variations. That comes from most asteroids are discovered near new moon when the sky is darker. And so around that time is when you'll have more known to be within radar range. And you see sort of a spike here in like November. This apparently is like a trend that has been seen before. And I'm told it's related to the weather in Arizona, since a lot of asteroids are discovered by surveys in Arizona. So in November, they'll have longer nights and less chance of precipitation. All right, so same thing for Canberra. So on most days, they wouldn't actually be able to see anything. The median, I guess, is 0, close to 1. So on maybe a third of the days, half to a third of the days, they could get at least 1 asteroid. Again, lower transmitter power, so if they had like a Goldstone style transmitter, the numbers would be similar. Okay, so Arecibo looks more promising. So again, on a median day, 15 asteroids potentially detectable. And then with something even better, so MGAT, around 75 potentially detectable. So again, it's that many within reach, but in practice, this is assuming 30 minutes of observations. So even if we did that all day, you could only get like 48 of them, or you'd have to budget the time very carefully. And I can imagine doing a marathon where you say, like, as soon as you hit an SNR of 5, we move on to another one, but that would be stressful, but interesting, I guess. Since our survey nights were like a few hours at a time, those were stressful enough, right, Louisa? And then Greenbank to NGVLA, so slightly better than NGAT, but again, in practice, they'd be limited by the fact that other people want to use the telescope. So finally, I think this is my last slide. So unique detectable near-Earth asteroids over a 12-month period. So any given asteroid is usually detectable for several consecutive days. So totals here, Canberra, I left off Canberra, they can get around 100 in a 12-month period. Goldstone around 370, so let's see, Arecibo 900, NGT and GBT each around 2,000, theoretically potentially detectable. Anyway, so yeah, stop there and take questions. Also, if anyone has thoughts on how to make these plots more comprehensible, I would appreciate hearing that. Like, this is sort of the best version I've come up with, but I know there's room for improvement. So thank you, and happy to take questions.
Very good. I mean, I think it's very easy to follow what you are telling on the figures and everything. And so just so that to clarify, if I correctly understand, the NGAT and GBT to NGDLA are theoretical calculations. They
Yeah.
do not exist. So that's still
Right.
Arecibo, the most sensitive and everything.
So yes, I mean, as you
The
say, these look
Arecibo
nice,
database
but they don't
one.
actually exist. So it's based on the
Yeah.
system specs and various publications. What goes into the calculations? I mean, I can imagine something that's like 10 megawatts of transmitter power as well, which is fun, but that doesn't exist either. Well,
Right, questions?
Yeah, it's a bit of the topic. I was wondering during your presentation, how the research will be affected by the new discoveries in the near future about using an SST, for instance.
okay.
How will affect.
Yes, good question. So more discoveries will mean more potentially detectable asteroids. This is just using like discoveries over like the past year. But it's one thing I wanted to explore more. So this is a paper I need to write up, possibly doing a follow-on paper, work through LSST and or NEO Surveyor. Like they have people on both those teams who've estimated like what population we expect to discover, how many asteroids. So basically to do that sort of calculation, I need to know like the orbital elements for the asteroid and the like simulated date at which it would be discovered. So yes, good question. I want to explore that, but I haven't done that part yet.
Okay.
So ask again in a year or two. My long list of things that I should work with.
All right, any other questions? Any questions from online participants?
I was wondering, what's the, average rotational period of the NEAs? Is it like 7 hours?
I mean, typically a few hours, actually, I don't have that plot in this presentation. Ask me a little later. I can find the, like, I did that analysis for like the ones we observed from Arecibo, like a couple hundred asteroids, just so I could sort of get the average properties for these calculations. But typically a few hours.
What's the fastest? What's, is there one that?
2019 okay was up there, right?
Yeah,
And
fastest,
Yeah.
observe is 30 seconds.
yeah, from your paper.
So that's like another, but,
Violent is a harsh word,
I mean.
but yeah, it could be
That's
something that is being held together by other forces that
For basic
by
purposes,
gravity. or
sometimes
it's by
after-
forces, but- That's my
Okay.
paper, that's under review, the
Okay,
20 fastest rotators and their collision.
well, okay, I love the review.
So the current, the technology still favors radio radars. For example, you have femtosecond pulses, pulse lasers. Can you use those for detecting?
I'd say, what's your continuous power there? I think the radar has to win,
Yeah.
because I don't think you can use a laser to transmit like 0.5 megawatt continuously.
They have terawatts.
Like, that's the pulse though, right? What's the time average? Because that's what matters for the SMO.
Yeah, I was gonna ask you a related question, you obviously have a model of radars that you use because you run these simulations. And there's a trade-off between, resolution and, how much power you can put out and all those things. Do you have like man, if we could build a radar, like this frequency, I could get the resolution to see, maybe a little bit deeper into the, those cracks and crevices.
Yeah, well, okay, that's tricky. So for like rocky materials, the radar will penetrate to around 10 times the wavelength. So if you want to see deeper, you want lower frequency,
Yeah.
but we want higher frequency to push the gain higher, so your beam is more focused. So that's a trade-off.
And in your simulation, I noticed that the small satellite asteroid had a lot higher RCS, I guess.
Yeah,
That seems like,
it looks brighter because it's like smaller overall, but the signal is compressed into like a smaller proportion of pixels than the primary. So yeah, that's a little misleading.
okay,
Or at least not misleading, but confusing, and just like one of those things we have to remember when we look at the radar images.
Yep.
But yeah, so, I mean, and like we ran into this issue when we were thinking about what exactly do we want for the radar system on like NGA or something else. There's like a continuum of objects you can observe, so it's not like there's a hard cutoff where it's like 1 megawatt is great, but like 900
Yeah.
kilowatts would be terrible. It's continuous, so if you increase the transmitter power, you'll get more and more objects.
do you do pulse compression? And you, I mean, use waveforms that, you know, are pulse compressed to get,
Okay, so it's continuously transmitted, so usually for a receiver, we modulate the phases, Goldstone, they can modulate the phase or do like linear frequency modulation.
like a P4 or something, yeah, okay.
Yeah, both chirps, but yeah. So again, either one works, that gives you the time structure coming back.
The bistatic data that they had, do they do that a lot?
Well, those are trickier because then you have to
Yeah.
schedule like the two facilities,
Yeah.
like Green Bank has other astronomers who want to use it, NGVLA will have probably even more astronomers who want to use it, so like the scheduling is tricky. Like we team up with Green Bank sometimes, but again, depending on their schedule, sometimes that's easier, sometimes not. I think like early 2020, it's like the weather in West Virginia was like cloudy and damp enough that they couldn't do many high frequency
Yeah.
observations. So that particular time it was easier for us to coordinate with
Yeah.
them.
Interesting.
That's the sort of thing that varies. And again, you're coordinating between two different facilities, possibly two different institutions. So in this case, they both be like sort of NRAOs, so maybe it would be a little easier to schedule, but again, they'd still have heavy demand.
Can they run a higher PRF since it's not, you know, the transmitting side is not receiving? This is the,
That's, so usually we'd switch between transmitting and receiving that,
oh, you swap the two sites like back and forth?
oh, no, sorry.
When you're running bistatic, sorry.
For monostatic, we transmit, then as the echoes are about to
Yeah,
come
yeah.
back, switch to receiving, yeah.
But you wouldn't have that constraint if you were bistatic.
Yeah,
We were the only transmitter with the green band. They didn't have a transmitter at the same band that we were operational in that moment. I think at some point Goldstone and RSU had the same band that they could transmit and receive, but RSU was the most powerful.
Right.
yeah. Well, and to answer your question, Goldstone could do faster modulation. That's like a property of the klystrons, but switching to bistatic doesn't really gain you anything that way. They could do their fast modulation in either case, monostatic or bistatic.
Yeah.
All right,
All right, thank you.
any other questions? Okay, great discussion, great presentation, thank you, Tom.
Thank you, Sean.
Thanks for